Hello. Today I'll be talking about glycolysis, which is the topic in biochemistry. I didn't really like biochemistry when I was a medical student, but after going through medical school, I realized just how important biochemistry can be. So I decided I could just visit back and try and make myself learn about biochemistry and hopefully coming out, you know, really enjoying it. So this is just the start, and I hope you can sort of um, walk with me with this little journey that I'm going to have. Okay, let's start learning about glycolysis. I'm going to try and keep things very, very simple, and I'll try and build it up using the same diagrams, but with more informations as we go on. So let's start. Glycolysis obviously starts with glucose, right? So glucose, the first step upon entering the cell, it will be converted into glucose 6-phosphate by the use of an enzyme called hexokinase, using 1 molecule of ATP per glucose. The interesting thing about this step is that it uses ATP. It has to spend an energy to convert this glucose into glucose 6-phosphate, but it has a very good reason why this has to be done. It sort of commits this glucose into entering the glycolysis because the cell membrane doesn't have a G6P transporter, which means that once glucose gets transported into the cell membrane, through the cell membrane, and it converted to glucose 6-phosphate, it can't leave the cell. So this glucose 6-phosphate, I can say that it's been committed, and G6P is like, okay, I'm ready to go into glycolysis. There's no turning back. Next step, the second step in glycolysis is glucose 6-phosphate converting into fructose 6-phosphate using an enzyme called phosphoglucoisomerase. This enzyme has the name isomerase in it, which means that it suggests the conversion of something that is an isomer or one thing into an isomer of itself. So glucose and fructose is an isomer. So this reaction is actually freely reversible, but usually it goes towards the direction of G6P to F6P because F6P is continuously being absorbed or changed into the F16BP by the next reaction. Let's move on. So the next step, the third step of glycolysis is F6P going into F16BP or fructose 1,6-bisphosphate by using this enzyme called phosphofructokinase. This enzyme is super important in glycolysis, but I'll discuss about why phosphofructokinase is very, very important in the coming presentation. So stay in tune. So you might have noticed that phosphofructokinase also has the name kinase. So you can guess that this reaction is also going to expend 1 ATP. Moving on to the next step. The fourth step is 1 F16-bisphosphate is sort of cleaved into dihydroacetone phosphate and glyceraldehyde acetone phosphate. So this is done by the enzyme aldolase. The fifth step is the conversion between DHAP, the dihydroacetone phosphate, and GAP, the glyceraldehyde acetone phosphate, by an enzyme called triphosphate isomerase. Again, the word isomerase is coming in. So basically, they probably have the same molecular formula, just different positions of each other. As we move into the sixth phase of glycolysis, we enter what is known as the payoff phase. So whenever ATP has been involved so far, it has always been an expenditure. So you had to spend energy all the while until now. And now, finally, we will get back those ATP. So it's like starting a business, you have to make some investments. So you have to actually pay money to start off a business. But after a while, you get that money back so that you get a profit. Same as in the glycolysis, you need to first spend the ATP in order to get more ATP back. So in this step, we enter the payoff phase by the GAP, or the glyceraldehyde acetone phosphate, turning into 1,3-BPG 1,3-bisphosphoglycerate, and it uses triose phosphate dehydrogenase. And also it would spend 1 molecule of NAD plus to make 1 molecule of NADH. We come across this molecule called NAD plus and NADH. Actually, this molecule is also very, very interesting. They actually gets involved in the electron transport chain, which is the more deeper sort of reaction to make energy. And I sort of like to think that sometimes I get sort of confused whether NAD plus is the more the form with more energy, or NADH is the form with more energy. I like to think that to try and remember this, like NAD plus is like medical students. We're all positive, optimistic. But then we go through like medical school, 5 years of grueling studying, and we are not very positive anymore. But we're more useful. So NADH is the more useful thing, which has more energy, whereas NAD plus is the precursor. So that's how I try to remember it. Okay, so moving on to the 7th phase of glycolysis is the conversion of 1,3-BPG to 3-phosphoglycerate. And we get 1 molecule of 1 ATP. And again, we come across this kinase, so phosphoglycerate kinase. But in this case, we actually earn 1 molecule of ATP. Yay! All right. Going on to the 8th step of glycolysis, which is the 3-phosphoglycerate becoming into 2-phosphoglycerate using an enzyme called phosphoglycerate mutase. So this enzyme is called a mutase. This phosphoglycerate, 3-phosphoglycerate and 2-phosphoglycerate probably has the same chemical formula. It's just that the phosphate group in this phosphoglycerate is in a different position, and for this to happen, a mutase. So it's like it's turning into a mutant of itself, which is basically the same thing but differently configured. The next step is basically 2-PG turning into PEP, phosphoenolpyruvate, by an enzyme called enolase. And the final step for glycolysis is PEP turning into pyruvate, finally. And we also get 1 molecule of ATP. So the enzyme is pyruvate kinase. And it's really easy to remember because, again, we have the ATP and we have the kinase. And we have pyruvate from pyruvate kinase. Perfect. So I'm going to stop this presentation for now. And I'll be following up with more stuff later when I come back. Thank you very much and see you next time.